All right, so today we're going to jump into something really cool, something that's at the heart of a lot of modern AI, reinforcement learning. We're basically going to build the whole idea from scratch, you and me. We'll look at how a machine can, well, learn just by trying things out, failing, and trying again, kind of like we do. Okay, so here's the plan. First, we'll meet the main characters of this story. Then, we'll see how they talk to each other, figure out what their goal is, and see what kind of problems they can solve. And to wrap it up, we'll get into the really neat part, how they learn to think ahead. Sound good? Let's get started. So let's just start with the big, fundamental question here. How does anything learn from just doing? Think about it. A baby learning to walk, you picking up a new video game, it's all just trial and error, right? You try something, it doesn't work, you adjust. The big puzzle for reinforcement learning is, can we build a machine that learns exactly like that? Okay, so to get our heads around this, the whole framework is built on two key players. You can think of them as the two main characters in a play. And honestly, every single bit of learning that happens, it's all about how these two interact. So first up, we have the agent. This is our learner, the one making the decisions. It's the brains of the whole operation. This could be the AI in a video game, the program flying a drone, or the code that's trying to get a robot to walk. The agent is the one that's always asking, okay, what's my next move? And then you've got the other half of the puzzle, the environment. This is literally everything else, everything the agent interacts with. So if your agent is a chess AI, the environment is the board, the pieces, and the opponent. If the agent is a robot, the environment is the room it's in. It's the world, the problem, the thing that pushes back and reacts to whatever the agent does. All right, so we've met our two players, the agent and the environment. The key thing to get is that they aren't just sitting there. Nope, they're locked in this constant back and forth, like a conversation or a dance. And this cycle is where all the learning happens. And this loop right here, this is the engine of reinforcement learning. Seriously, it's that simple, but it's incredibly powerful. The agent does something, the environment reacts, the agent sees that reaction, and then it does something else, over and over and over. This is how it learns, from pure, raw experience. So let's break that loop down step by step. Okay, so at any point in time, let's just call it time t. The agent looks at the world. It sees the current state. Based on that state, it decides to take an action. Then, the environment comes back with two crucial pieces of information. First, a reward. Think of it as a score, like good job or bad job. And second, the new state of the world. And boom, the loop starts right over. You know what? Let's make this super concrete with an example. Imagine we've got a little robot, and its whole job is to roam around and pick up empty soda cans. So right now, what's its state? Well, let's say it's just one piece of information. Its battery is at 50%. That's all the agent knows about the world at this moment. Okay, so the agent, which is just the robot's brain, its software, sees that 50% battery level. It has choices, right? It could go searching for cans, it could play it safe and head back to its charger, or it could just wait. For now, let's say it takes an action. It decides to go search for cans. And now, the environment responds. See, searching takes energy, so the environment gives it a little bit of feedback, a reward of -1. That's like a small penalty for using up power. And what's the new state? Well, its battery is now down to 45%. And there you have it. One full turn of the loop is done. The agent just learned a tiny little lesson. Searching costs energy. Okay, so this is all making sense, right? The agent acts, it gets rewards. But that brings up a really, really important question. What's the point of it all? What is the agent actually trying to do? How does it know what a good job even looks like in the long run? Well, the answer is a huge idea in this field. It's called the reward hypothesis. And it's actually pretty simple. It basically says that any goal you can think of, winning a game, driving a car, anything, can be boiled down to one single thing, getting the highest possible total score over time. So the agent isn't just trying to get a quick reward right now. No, it's playing the long game. It wants to maximize the total reward it gets forever. And this quote here just nails it. The reward signal is how you tell the robot what you want, not how to do it. Think about our recycling robot. We don't write code that says turn left, go forward, scan for a can. No way. We just give it a big, juicy +100 reward whenever it puts a can in the recycling bin. We define the goal, the what, and the agent has to figure out the best strategy, the how, all on its own.
So, if the goal is to get the most reward possible, the agent needs to know what kind of game it's in, because not all problems are created equal. Some have a definite end, a finish line, and some, well, they just keep on going.
And that gives us two main flavors of tasks. On one side, you have episodic tasks. These are things that have a clear start and a clear end. A game of chess is a perfect example. You play, someone wins, or it's a draw, and the episode is over. Then you start a new one. But on the other side, you have continuing tasks. These just go on and on forever. Like imagine an AI managing the temperature in a building. Its job is never done. It just has to keep doing a good job indefinitely. Okay, and this is where it gets really interesting. If the agent wants to maximize its total reward, it can't just be greedy and grab the first reward it sees. It has to be smart. It has to think about the future. Sometimes taking a small hit now, like our robot using a bit of battery, could set it up for a massive payoff later on. So we have a name for this idea of total future reward. We call it the return. Let's just use the letter G of t, where t is the current time. The return is just the sum of all the rewards the agent is going to get from this moment on. So for an episodic task like chess, it's pretty simple. It's just all the points you get until the game is over. And this value, this return, is what the agent is really trying to make as big as possible. But wait a second. This leads to a big problem, doesn't it? What about those continuing tasks, the ones that never end? If the agent keeps getting, say, a +1 reward forever, well, the total sum is going to be infinite. And how on earth do you maximize something that's infinite? It doesn't make sense. It's a real mathematical puzzle we gotta figure out.
The solution is actually super clever, and it's called discounting. It's based on an idea we all understand instinctively. Getting $10 today is better than getting $10 next year, right? We're going to apply that same logic. We'll just make rewards that are far away in the future worth a little bit less than rewards we can get right now.
And here's how we do it with this formula. Let's walk through it together. It's not as scary as it looks. On the left, G_t, that's our goal, the total discounted return we want to figure out. Okay, so it starts with the very next reward, R_t+1. We take that one at full value. Then we add the next reward after that, R_t+2, but look, we multiply it by this little Greek letter gamma. That's our discount factor. Then for the reward after that, R_t+3, we multiply it by gamma squared. See the pattern? The further out the reward is, the more times we multiply it by gamma. And here's the trick. Gamma is always a number between 0 and 1. So when you keep multiplying by a number smaller than 1, the result gets smaller and smaller and smaller. This neat little piece of math guarantees that even if the series goes on forever, the total sum will add up to a nice finite number. Problem solved. So this gamma, our discount rate, is a dial we can tune. It's a number we pick somewhere between 0 and 1, and it basically sets the agent's personality. If we set gamma to 0, the agent is totally myopic. It can only see what's right in front of its face. It only cares about the immediate next reward. But as we crank gamma up closer to 1, the agent becomes more and more farsighted. It starts to care a whole lot about rewards way down the road.
And this chart really drives the point home. Let's say we set our gamma to 0.9, so our agent is pretty farsighted. A reward of +10 that you get right now, it's worth a full 10 points. Simple. But now look at the middle bar. If you have to wait just 5 steps to get that same +10 reward, its actual value to the agent drops to about 6. And if it's 10 steps away, it's only worth about 3.5. It's the exact same reward, but its perceived value just plummets the further out you have to wait for it. It's all about that timing. So let's take a breath and recap. We've got our agent, our learner. We've got our environment, the world it lives in. We know they talk to each other in this constant loop of state, action, and reward. And most importantly, we now have a rock-solid definition of the agent's goal. Maximize the total discounted reward. We've perfectly framed the entire problem. But that leaves us with the million-dollar question, doesn't it? We know what the agent wants to do, but how does it actually learn the best strategy to pull it off? And that is the question we'll start to answer next time.